Alrighty, moving onward. I believe we are on Chapter 20, Section 2, turning our single-threaded server into a multi-threaded server. Okay. That. Right now, the server will process each request in turn, meaning it won't process the second connection until the first is finished processing. If the server received more and more requests, this serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished, even if the new request can be processed quickly. We'll need to fix this, but first, we'll look at the problem in action. Alright, so what basically they're saying here is that our current server only deals with requests one at a time, and because it's a serial, like one after the other execution of processing these requests, that can run into a number of issues, and naturally we want to make this multi-threaded or be able to process multiple connections at once. Simulating a slow request in the current server implementation. We'll look at how a slow processing request can affect other requests made to our current server implementation. Listing 20-10 implements handling a request to /sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. And let's see what they have here. Thread, time duration, handle connection, get/sleep, so they have an explicit endpoint for /sleep, and that's probably here. Buffer starts with sleep, thread, sleep, 5 seconds, and then return the page. Alright, I think we can add that real quick. Let's see, I'll move that to the side so I can see both. They did add 2 imports. Use std thread. Oh, I spelled use wrong. Use std standard library. Time duration. Okay. And in handle, we have something after get, which we have sleep. So let sleep equal, and I'll just copy and paste this part. Copy paste, which is just get endpoint /sleep, and then the HTTP protocol. And then down here, before the last else, they had an else if, and buffer dot starts with sleep. Move this over, and if it starts with sleep, I can type that out. I'll just copy it. We have a thread sleep and we have a duration of 5 seconds. And then after that, we return the page. So now that we have it here, let's test it out. Cargo run. And let me see if I remember what this is being put on. It's being bounded to localhost 7878. Cool. Localhost 7878. Here's the regular page. And now here is the sleep page. And you see it waits 5 seconds before it does anything. And now it resolved. Just so it's clear, let's do that from an empty page. or a 404 page. Right? And then if we go to sleep, you can actually see the waiting. Now it's visually apparent when it changes. Yeah. That seems to work properly. Turn off the server. Let's go back. This code is a bit messy, but it's good enough for simulation purposes. We created a second request sleep, whose data our server recognizes. We added an else if after the if block to check for the request to sleep. When the request is received, the server will sleep for 5 seconds before rendering the successful HTML page. You can see how primitive our server is. Real libraries would handle the recognition of multiple requests in a much less verbose way. Oh, that's one thing we didn't even bother to check. That skipped my mind. Multiple requests, not just one. So let's run the server again. We have this here, and then here we can do the let's do the 404 page. That'll work out. So I believe what they're trying to show us is that while this request is going, this request will not go. Ooh, this request has to wait till the first one is done. And you see they resolve at roughly the same time. So let's do that again. You can see it going here. This one's still going, and then it resolves roughly at the same time. That is to show that the second request is waiting for the first one to be done. Now that that's over with, let's get back to the book. You can see how primitive our server is. Real libraries would handle the recognition of multiple requests in a much less verbose way. Start the server using cargo run. Then open two browser windows, one for localhost 7878 and the other for localhost 7878/sleep. If you enter the URI a few times, as before, you'll see it respond quickly. But if you enter /sleep and then load the root URI, you'll see that the root waits until sleep has slept for its full 5 seconds before loading, which we did see when we ran the test just now. There are multiple ways we could change how our web server works to avoid having more requests back up behind a slow request. The one we'll implement is a thread pool. Improving throughput with a thread pool. Okay? A thread pool is a group of spawn threads that are waiting and ready to handle a task. When the program receives a new task, it assigns one of the threads in the pool to the task, and that thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processing. When the first thread is done processing its task, it returns to the pool of idle threads, ready to handle a new task. A thread pool allows you to process connections concurrently, increasing the throughput of your server. All right, so here they're going over, we can recap the definition of thread pool that they gave us, right? So in the model of a thread pool, we have 5, let's call them workers. Well, I said 5. 5 is an arbitrary number for my example, but imagine that we have 5. We can have as many as we want or as few as we want. Imagine we have 5 workers that are ready to take on a task. When the first request comes in, one worker is going to go out, handle that task. If that worker is done with that task, he returns to the pool. If that worker is not done with that task, then obviously still working. So if that worker is still working on a task and another request comes in, well, there are now 4 workers left that can handle the new request. And one of those 4 workers goes and handles that. And so on until you either run out of workers that can handle things or they just recycle. But you get the general idea. More or less, you have ways of handling multiple requests at a time because you have things that can handle them separately. We'll limit the number of threads in the pool to a small number to protect us from denial of service attacks. If we had our program create a new thread for each request as it came in, someone making 10 million requests to our server could create havoc by using up all our server's resources and grinding the processing of requests to a halt. So this is a very real thing, denial of service, and denial of service just means that when other people that are trying to get to your website for real reasons, like your natural traffic, the traffic that you want, and they can't get to your site because your site is down for many reasons, but more or less you ran out of resources and you don't have enough resources to serve them. And one way to run out of resources is to have each request be handled by a new thread, and then have somebody send 10 million requests to your server. Because now you have 10 million threads, and because you have just used, each thread is using resources of your machine, you just ate up all the resources of your machine. And now when a new request comes in, nothing can happen because your machine is just running dead slow. It's a bad situation to be in, honestly. But to avoid that, you have to, or you should, limit the number of threads that you're allowed to use. And in my example earlier, I had it 5, but you can probably use much more than that. However, you wouldn't want to use an infinite amount of threads. Rather than spawning unlimited threads, we'll have a fixed number of threads waiting in the pool. As requests come in, they'll be sent to the pool for processing. The pool will maintain a queue of incoming requests. Each of the threads in the pool will pop off a request from this queue, handle the request, and then ask the queue for another request. With this design, we can process n requests concurrently, where n is the number of threads. If each thread is responding to a long-term running request, subsequent requests can still back up in the queue. But we increase the number of long-running requests we can handle before reaching that point. Alright, so they're going over kind of what I did earlier where I said I only have 5 requests in my pool. 5 workers in my pool. And they're explaining the model in a little bit more detail. So the requests are going to come in. They're going to be put into a queue, right? And then each of these workers, in my example I have 5, will pull from the top of the queue, work on that task, and then come back and then request a new one. Now, in the scenario where all of your available workers are currently working on a task or working on a request, the server can still be backed up and requests can still be forced to wait. But what this is doing, at least this technique, is it's allowing us to process more long-running requests before reaching that point. So earlier we did it with 2 requests. We did one to sleep and then one to for pillow, whichever one you want. And the second request had to wait till the first one finished. Now we have up to 5 requests that we can have running before we have to wait. This technique is just one of many ways to improve the throughput of a web server. Other options you might explore are the fork/join model and the single-threaded async I/O model. If you're interested in this topic, you can read more about other solutions and try to implement them in Rust. With a low-level language like Rust, all of these options are possible. Pretty much here they're saying that this is not the only solution to the problem, like the one that we've been illustrating. Other ones include fork/join model, which I don't know explicitly off the top of my head. And then you have the single-threaded async I/O model, which is becoming really popular. And Rust has it as well, but Rust has both of these options. But I don't know enough of that to speak on it off the top of my head. Moving onward. Before we begin implementing a thread pool, let's talk about what using the thread pool should look like. When you're trying to design code, writing the client interface first can help guide your design. Write the API of the code so it's structured in a way you want to call it. Then implement the functionality within that structure rather than implementing the functionality and then designing the public API. Sure, they're pretty much stating that in terms of architecture and designing things, you should know what your end product should look like before you just implement all the little details. And for us, at least in this example, that would mean writing out the API structure first and then writing the code that implements the API. Okay. Similar to how we use test-driven development in the project in Chapter 12, we'll use compiler-driven development here. We'll write the code that calls the function we want, and then we'll look at errors from the compiler to determine what we should change next to get the code to work. Alright, so what they're suggesting here is compiler-driven development, which is a term I've only really heard in Rust, and I've actually never done it myself. But the idea is write out the outline of your code, run it, see what the compiler tells you is the issue, fix that issue, run it again, see what the compiler says, fix that next issue, and so on and so forth until it starts working. At least that's my understanding of it. We'll see. We'll see how it goes. Code structure if we could spawn a thread for each request. First, let's explore how our code might look if we did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point. Listing 20-11 shows the changes to make to main to spawn a new thread to handle each stream within the for loop. Alright. We still have our listeners binding to 7878. And oh, yeah, they just use thread spawn. They have their closure, and within the closure calls handle connection. Yeah, that's pretty straightforward. Let's do that now. Ooh. Let me minimize this. Thread has already been added to our imports list. So here. Thread spawn our closure, and then we move this into the thread. And voila. To test this out, we should be able to run the server and do the same example. So ready, set, go. And that already responded, is done, and this is still going. And now this is just concluded, the sleep one. So yeah, even though this was called second, it finished first in terms of being rendered and ready. And that's because we added threads. All right, close that. As you learned in chapter 16, thread spawn will create a new thread and then run the code in the closure in the new thread. If you run this code and load /sleep in your browser, then / in 2 more browser tabs, you'll indeed see that the requests to / don't have to wait for /sleep to finish. But as we mentioned, this will eventually overwhelm the system because you're making new threads without any limit. Yes, great warning. And we did get to see this. We didn't use their example of the root and then sleep. We used sleep and a 404 page, but yeah, same diff. Creating a similar interface for a finite number of threads. We want our thread pool to work in a similar, familiar way, so switching from threads to a thread pool doesn't require large changes to the code that uses our API. Listing 20-12 shows the hypothetical interface for a thread pool struct we want to use instead of thread spawn. Hypothetical. Let's look at this. The bind is still here. Thread pool for I said 5 in my example, they gave us even less. 4, got it. 4, and then thread pool execute, and then the handle connection. So this is almost identical. And I don't know that was compiled and work, but it's easy to write. thread pool. Does that need to be imported? I don't know. Let's check. Use standard library thread. Nope, I don't see it there. And then if I did something like let pool equal thread pool, yeah, I don't see it there either. So hypothetically speaking, I'm not sure if the way they're calling it exists. But let's see. We use thread pool new to create a new thread pool with a configurable number of threads. In this case, 4. Then in the for loop, pool.execute has a similar interface as thread spawn in that it takes a closure the pool should run for each stream. We need to implement pool.execute so it takes the closure and gives it to a thread in the pool to run. This code won't yet compile, but we'll try so the compiler can guide us in how to fix it. I see. So yeah, that's not supposed to exist. Okay. That being completely known now, let's write what they had there. Let pool equal thread pool new 4, and in here is pool.execute. Oh, they also want us to run it to see what kind of errors we're going to get. Forgot about that. So yeah, thread pool doesn't exist. And that was the first main one. I'm not seeing anything else here. Okay. Building the thread pool struct using compiler-driven development. Make the changes in listing 20-12 to your source.main. And then let's use the compiler errors from cargo check to drive our development. Here is the first error we get. They use cargo check. I haven't used cargo check before. Cargo check. Okay. I guess it just compiles it but doesn't run it. That would make sense. They got the same errors we did. Great. This error tells us we need a thread pool type or module. So we'll build one now. Our thread pool implementation will be independent of the kind of work our web server is doing. So let's switch the hello crate from a binary crate to a library crate to hold our thread pool implementation. After we change to a library crate, we can also use the separate thread pool library for any work we want to do using a thread pool, not just for serving web requests. Create a source/lib.rs that contains the following, which is the simplest definition of a thread pool struct that we can have for now. Okay, so they're using this error to guide us. This error states that this thing doesn't exist, so we need to define it. And because we're defining it, and this is not necessarily directly integral to our application, like our web server, this can go into a library or a shared place that we could use in other places. So they want us to make this into a library crate as well by adding a source.lib.rs file and then putting this in it, and that would create it, I believe. So let's work on that. Source new file lib.rs cancel, and then here, that's all we want. And to be clear, when we run this code now, oh, I don't think we imported it. They called it hello. I don't know what mine is called. That might be an issue. Ooh. Rust hello server. Oh, I have a long name for this. That's gonna suck. Use Rust hello server thread pool. Alright, and if I do cargo check, we see a different error. Yes, and this error is saying that the function or associated item not found. So new is not defined. So let's go back here. I think we jumped a little bit. We're right here. Then create a new directory source/bin and move the binary crate root. Wait, what? They want me to move what? Oh, yeah, I definitely didn't do this. Then create a new directory source/bin and move the binary crate rooted in source/main into source/bin main.rs. Doing so will make the library crate the primary crate in the hello directory. We can still run the binary in source/bin/main using cargo run. After moving the main.rs file, edit it to bring the library crate in and bring thread pool into scope by adding the following code to the top of your source/bin/rs file. So yeah, I definitely didn't do that. Let's do that now. So they want me to create a bin and then move main there. Okay. New directory. Call it bin. And then drag that. Yes. And I already did the importing. So let's run this and see if it does the same error. Cool, everything's kosher. This code still won't work, but let's check it again to get the next error we need to address. And we did that. That error is the new. This error indicates that next we need to create an associated function named new for thread pool. We also know that new needs to have one parameter that can accept 4 as an argument and should return a thread pool instance. Let's implement the simplest new function that will have those characteristics. All right, here we have public struct thread pool, which we already did, and we have the implementation block. We create our new function. We have a size, which is uSize, and then we return thread pool, which doesn't really do anything yet, but it's the minimum amount of code that will work. That will make us move on to the next error. That makes sense. Let's do that now. And let's run this. Pool.execute. That's the next error. We choose uSize as the type of the size parameter because we know that a negative number of threads doesn't make any sense. We also know we'll use this 4 as the number of element in the collection of threads. This is what the uSize type is for, as discussed in the integer type section of chapter 3. And uSize, if you don't remember, are just positive numbers. It can't be negative. Or else we use, I think, iSize. That's the other one. It's been a while. But yeah, you can review that in chapter 3. Chapter 3 was a long time ago. Anyway, let's check the code again. We did that. I didn't see that first error. I only saw the execute. Let's revisit. Oh, yep. There is the size thing here. It's saying that we should probably use it with an underscore because it's not being used. Is that what they have here? Yeah, unused. Cool. Now we get a warning and an error. Ignoring the warning for a moment, the error occurs because we don't have an execute method on thread pool. Recall that the creating a similar interface for a finite number of threads section that we decided our thread pool should have an interface similar to thread spawn. In addition, we implement the execute function, so it takes the closure it's given and gives it to the idle thread in the pool to run. They're just telling us to remember what the plan is. The plan is to make sure that we adhere to this API, the thread spawn, meaning that execute just takes a closure that we can pass directly into the underlying thread. We'll define the execute method on thread pool to take a closure as a parameter. Recall from the storing closure using generic parameters and the FN traits section in chapter 13 that we can take a closure as parameter with 3 different traits: capital FN mute, capital FN once. We need to decide which kind of closure to use here. We know we'll end up doing something similar to the standard library thread spawn implementation, so we can look at what bounds the signature of thread spawn has on its parameter. The documentation shows us the following. Alright, so basically what they're stating here is that yes, we decided that we're going to adhere to the thread spawn implementation. Like whatever closure they need, we have to be able to accept that and pass it directly to them. In order to figure out what they need, we can just look at their source code, and they have like a little snippet down here, and it looks like it's a function once and send, which I don't think we have to do anything with send, but yeah, okay. The F-type parameter is the one we're concerned with here. The T-type parameter is related to the return value, and we're not concerned with that. We can see that spawn uses capital FN once as the trait bound on F. This is probably what we want as well, because we'll eventually pass the argument we get in execute to spawn. We can be further confident that capital FN once is the trait we want to use because the thread for running a request will only execute that request closure one time, which matches the want in capital FN once. So here we're just identifying that the spawn implementation uses the FN once, and if we wanted to think about it for a second, if we stopped and thought about it for a second, the requests are only happening once, so that kind of makes sense that we're using the once trait. The F-type parameter also has the trait bounds send and the lifetime bound static, which are useful in our situation. We need send to transfer the closure from one thread to another, and static because we don't know how long the thread will take to execute. Let's create an execute method on thread pool that will take a generic parameter of type F with these bounds. Okay, so that's one thing I didn't really understand at the time, but they explained it here. We need send because we need to be able to send this thing to different threads. And we need static because we are not sure how long this thing is going to take to run. I guess we just want to ensure that it's still alive. Sure. So down here we're going to write our execute implementation, at least the bounds. And public function execute, we have F and F here, small f, where f is bounded by the capital FN once plus send plus static. Okay, that makes sense. We just copy that. Lib right here. We still use the parentheses after capital FN once because this FN once represents a closure that takes no parameters and returns the unit type parentheses. Just like function definitions, the return type can be omitted from the signature, but even if we have no parameters, we still need the parentheses. Okay, they're explaining this part. There are no parameters, but we still need the parentheses because it's syntax. Again, this is the simplest implementation of the execute method, where it does nothing, but we're trying only to make our code compile. Let's check it again. Okay, I'm getting a better understanding of this compiler-driven development. We use cargo check to keep hitting things to make sure it compiles, and then afterwards I guess we can run it. And this looked like it compiled, actually. Yeah. I think they got the same thing here. We're receiving only warnings now, which means it compiles. But note that if you try cargo run and make a request in the browser, you'll see the errors in the browser that we saw at the beginning of the chapter. Our library isn't actually calling the closure pass to execute yet. I'm kind of curious to see those errors, but at the same time, it doesn't really make sense. Note, a saying you might hear about languages with strict compilers, such as Haskell and Rust, is, if the code compiles, it works. But this saying is not universally true. Our project compiles, but it does absolutely nothing. If we were building a real complete project, this would be a good time to start writing unit tests to check that the code compiles and has the behavior we want. Okay, so they took a note to address some of the comments you hear about languages with strong compilers, and I've definitely heard this about Rust, not about Haskell, but I don't take part in the Haskell community, so yeah. But that saying is, if it compiles, it works. But that's assuming that you have code that does something. Right now, our code is just empty shells that compile because we're just trying to get it to compile, but we know it's not going to work. However, in terms of your project, they all state that this is a good time to write unit tests. So seemingly, if I can get this compiler-driven development in my head right now, you write the different code and do cargo check to make sure it compiles. Once it compiles, you write your unit test to assure that your functionality is what you want it to be. So you have like test-driven development. You have your unit test first. And then you write your implementation and make sure your tests pass. And then you run it. That seems like it would make sense in terms of a workflow.